Okay, record. Okay, so I think we're going ahead and started. I thought today we would start out with algorithmic information theory, and we would start with the lectures on that, so get a fresh start on a new topic. As I mentioned before, there's different models of information. As Claude Chan mentioned, he defined information in a way that made it applicable to communication. There are other ways to define information, and we actually talked about this in the beginning. Information can be modeled dependent on who you are and what you want to model it for. There's so-called Fisher information and probability. There's information that the physicists talk about, and their information is the information in the wave equation. And there was a big argument one time of whether information is destroyed as a result of black holes. And I don't know what the resolution of that was, but nevertheless, it was something which was kind of interesting. It was a different definition of information. So there's a bunch of different information. Of course, the most widespread of information is Shannon information. We're going to be talking about Kolmogorov information. I think I mentioned this previously, but there were three people that discovered Kolmogorov information theory. And they were Kolmogorov, Solomonoff, and Chaitin. And because Kolmogorov was already a famous Russian mathematician, his name stuck. So I'm going to try to refer to it occasionally as KCS information theory for Kolmogorov, Chaitin, and Solomonoff. Yes, and because I think that's more fair. It turns out that Solomonoff proposed it in a different sort of fashion, and it was Gregory Chaitin that came along and introduced it while he was a teenager. Believe it or not, in New York City. And I did a interview. Let me tell you a little bit about my background with Gregory Chaitin. I went to this talk one time, and I was just learning about Chaitin's number. And of course, I'm a professor, and I'm really smart, and I know everything. And so I went to this lecture, and this guy was talking about Chaitin's number. And I got to the end of the lecture, and he said, "Are there any questions?" And I raised my hand, and I said, "Chaitin's number is independent of the computer program that you use. Isn't that right? It seems to me that that's the case." And he said, "No, it depends on the computer program you're using." And I thought, well, I'm a smart professor, so I kind of poo-pooed it. And then he went on to another question. So I just let it slide because the guy was obviously ignorant. So I was on the plane coming back from the conference with a friend, Bill Dembski, and I was just understanding Chaitin's number, and we're going to get into Chaitin's number. I consider it incredible. I don't want to overbuild it for you, but it's an astonishing intellectual feat what he did. But I said, I would like to get into the mind I would like to meet the guy that came up with Chaitin's number. It is so astonishing, so wonderful. And Bill's eyes got big, and he looked at me and he said, that guy you were questioning? I said, yeah. He said, that was Chaitin. So it was Chaitin that was giving the lecture, and I was there questioning his number. And of course, he was right. But I shared that with Chaitin later on, and we became not friends, but certainly acquaintances. I did a interview with him, and one of the things I'm going to do is to make that interview available to you and let you listen to Gregory Chaitin, a living legend who's still alive. He's retired. He's living in Argentina. He is married. He just had a couple of kids and is a wonderful human being. And wonderful human being in the sense that he wrote this article one time which used algorithmic information theory to give a proof of evolution. Well, I looked at it and I thought, no, this is not true. What he was doing was akin to something we've talked about in here before. If you're given an oracle, you can extract different amounts of active information depending on how clever you are in addressing that oracle and sucking out information from the oracle. And that's exactly what Chaitin was doing with his algorithmic information theory. So a student of mine, Winston Ewart, and I wrote a piece that basically said that No, this is just sucking different amounts of active information out of a fixed oracle. And we gave an example of a Hamming oracle. And you could use Hamming oracles different ways. You could use the information that is given by a Hamming oracle in different ways. And that was that was good. So I sent a copy of the paper to Chayton because I figured, that was a fair thing to do. And he wrote back and he said, "This is wonderful. I really appreciate your work. In fact, when you get it published, let me know because I want to tell my students." So I thought, wow, that is really cool. Because usually when people criticize my work, my first reaction is defensive. I just want to make sure that my work is recognized for the genius that it is. But Chayton recognized the validity of our argument and actually backtracked a little bit. So again, we became acquaintances. I met him on a couple of other occasions, and we did a podcast together and went over a lot of the material that we're talking about here. So I think if you listen to it, there's a link to the podcast on the page, and I think you'll enjoy it because he's a really interesting guy. And the other thing I think I mentioned was the fact he did this when he got his first publication when he was 17 years old, for Pete's sakes. Uh, just an astonishing guy. So let's go ahead and let's talk about introductory remarks to KCS information theory or Kolmogorov information theory. Now, some of these slides are redundant from the slides that I presented in the computational intelligence class. So just bear with me because this is the actual foundation of computational intelligence. So I'm going to share my screen here. Share my screen. Okay, hopefully you can see this, right? Can you see my screen? Give me a thumbs up. Okay, good. And you can see the whole screen. It's not just the partitioned one. You can see the whole screen. Okay, good. This was the genesis of artificial intelligence, 1956, in a summer Dartmouth conference, where people got together and coined the word artificial intelligence. In fact, the guy in the back row on the right, who was John McCarthy, was the guy that coined the term artificial intelligence. To his right is our hero in this course, Claude Shannon. I mean, he was the one in 1947, 48 published the landmark paper, and we've spent a lot of time going over the fundamental results that he gave in his paper. Front row, second from the left, is with the receding hairline, is Ray Solomonoff. So he was one of the founders of algorithmic information theory, and some of his work we're going to be talking about here. So you can see there were really geniuses. In the middle of the back row is Marvin Minsky, who later on went and founded the Artificial Intelligence Lab at MIT. And so you can see there were really smart guys that started the genesis of artificial intelligence in 1950. Let's see, what was it? 1956. This was a few years before Shannon published his paper, so he was still working on it. Shannon did a lot of interesting work on artificial intelligence, like he was able to actually train artificial mouses to learn how to go through mazes, and he did this wonderfully. He also was the first guy that really tackled automatic winning at chess. And in fact, the strategy he came up with is still the strategy which is used in the modern chess artificial intelligence programs, which is to minimize the harm that your opponent can do to you. It's kind of a mini-max sort of problem. So this was the generation of artificial intelligence, and I put it up here mostly to talk about Ray Solomonoff as one of the guys that is the father of this sort of thing. And all these guys knew each other back then. So it all started with the Turing halting problem. We talked about this in computational intelligence as the first problem that was identified that could not be solved by a computer. It was non-algorithmic. And the basic idea behind the halting problem is as follows. You cannot write a program to analyze another arbitrary program to say whether that program stopped or ran forever. So it was called a halting problem. I give you a problem. Does it halt? Does it run forever? And I give you this algorithm, And the question is can you write another algorithm to analyze this step-by-step procedure to indicate that a program does stop or does start? Now, you're not implementing the program, because if you implemented the program and it never halted, you would never know it halted, right? So this program would identify some way that it halted or didn't halt. And again, for the not halting, you couldn't do that. So some people call this semi-decidable. Because if you were given an algorithm and you ran it and it halted, well, that was the answer. But if you gave somebody a program and it didn't halt after 1,000 years, you can say, well, it doesn't halt, but maybe it would halt after 1,000 years in 10 seconds, right? So you couldn't decide really whether a program didn't halt. And Turing showed that a halting problem cannot be written. The halting problem is non-algorithmic. And this is foundational to the core of algorithmic information theory, is there are things which are non-computable. And we're going to learn about so-called Kolmogorov complexity, or KCS complexity. And we're going to show, just interestingly, that KCS information is not computable. Wow. So we're going to deal with a whole subject where the actual fundamental measure can't be measured. However, number one, it's a good place and good way of thinking. Kolmogorov complexity is a good way of thinking. Number two, it is it is it's very useful in a number of other ways. It's a good way of thinking. And the second thing is it can be bounded. And we'll talk about why it can be bounded. And we can actually get our fingers on it. So a halting program cannot be written. A halting program is non-algorithmic. So here is the basic idea of the halting problem. Turing hypothesized that the Turing halting oracle is a program which can determine whether an arbitrary program halts or not. So I feed it any computer program, and it says it will either halt or it will run forever. Whoops. It will either halt or run forever. And this was a question which Turing addressed, and he showed that the halting oracle is provably non-computable. And actually, his proof is kind of interesting, and we'll talk about this in a minute. This went on and to be generalized in a number of other areas. We know now that there's lots of things that are non-computable. In fact, I'm in a dialogue now with a guy in Silicon Valley, George Meropoulos, and we're talking about the idea that AGI might be non-computable. And he has a very interesting proof of this, which I'm trying to devour. And we've had about 3 or 4 meetings, and we're going to continue the meeting until I get his idea. And then we're going to popularize it, because one of the things I'm good at is taking complex ideas and reducing them to fundamental examples. So hopefully watch out for that. So it could be AGI, artificial general intelligence, is not computable, at least by the definition that he is using. So let's take a look at this. Let's take a look at another generalization of the halting problem. This is Rice's theorem. It's a generalization of the halting problem, and it says all non-trivial semantic properties of programs are undecidable, including halting. So halting is one non-trivial semantic property of programs. What's another example? Another example is printing the number 3. You cannot write a general program to decide whether another program will eventually print the number 3 or not. That's another example of a non-trivial semantic property. So you can't decide a priori for anything. Now, clearly, if you have very simple programs like Hello World, you can analyze that and you can say, well, this is going to halt. But don't forget, the halting problem assumes that the halting oracle can be presented any program of any length, and that program will either be announced to be to halt or indeed to run forever. Now, what's interesting about this is determinism does not imply knowability. Before I talk about that, let me talk about the kind of intuitive idea of Rice's theorem. Take a program that we're not sure whether it halts or not. We're going to add one more line of code, and right before it halts, we're going to say print 3. So we have a program, and right before it halts, if it halts, it prints 3. If it doesn't halt, it doesn't print 3. So you can see that the idea of printing 3 is kind of a subset of this more general halting problem, because you can say, I can't tell you if you present the number 3, and I can take any halting problem, any problem I'm trying to say whether it halts or not, and put in the program right before it would halt, print 3. So if the program halts, it prints 3. If it doesn't halt, it doesn't print 3. So therefore, this is a generalization. Now, there's more complex examples of this, but I think you can see that indeed it makes sense that you can't write a computer program to say whether another computer program prints the number of 3, and it's because of the halting problem. Now, it's larger than that, but nevertheless, this is very interesting. Now, the other thing which is interesting philosophically is that determinism does not imply knowability. Now, before quantum mechanics, Laplace, and you're familiar with Laplace, with the Laplace transform, the Laplacian in vector calculus, and the Laplacian distribution and probability theory. Laplace, when he was alive, says, you know what? I'm a determinist. If I knew the position and the velocity and the location of every little particle in the universe, I could forecast the future. In other words, if there were determinism in the universe and I knew everything about the universe right now, I could forecast the future. Now, what Rice's theorem shows is that no, you can't, because a program which I present to the halting oracle is totally deterministic. Computer programs can't generate random numbers. So even if a random number is in there, it's a pseudo-random number. And so everything is deterministic. It's deterministic. And yet, even though it's deterministic, we can't tell what the future is. We can't tell whether that program halts or not. So Laplace was right, even under the assumptions of the time he existed when he lived. He lived in the time of determinism in terms of Newtonian mechanics and everything else. He wasn't aware of quantum theory, for example. But even then, there's some people that say, well, there's still determinism if you're given the location of all the particles in the universe and all their wave functions. You could determine the future in a probabilistic sort of way. So they still have this determinism, this idea that the future can be presented from the present. But no, you can't. Even though interestingly, the wave function is deterministic. Even if you knew all of the wave functions and everything, the future is not available to us, because we can't tell from a deterministic list of rules what is going to happen. That's what Rice's theorem shows. If we have a deterministic set of rules, which is a computer program, we can't tell some trivial things that are going to happen in the future. So determinism does not imply knowability. This is, to me, a great philosophical smackdown, in that determinism does not allow you to forecast the future. That is, I think, really, to me, that's fascinating. I hope you find it fascinating too. So this is Pierre-Simon Marquis Laplace, who was famously an atheist at the time. Uh, well, there's a lot of people that were atheists. Claude Shannon was an atheist, for example. But there was a lot of them that believed in God. It turns out that the intellect and a person's faith are not correlated. You have incredibly smart people like Newton, Euler, Faraday, Maxwell, who are all believers in God, and they all happen to be Christian. And then you have people like Laplace and Claude Shannon who are atheists. Now, clearly these people have IQs which are off the chart, but their IQ does not correlate with their degree of belief in faith in God. So I've always found that interesting. And you can come down to somebody with a 2-digit IQ, and it's easy for them to believe in God, or easy for them to not believe in God. So intellect is not correlated with the degree of faith that one has. It used to be that people would say, well, the smarter you are, if you're really, really smart, you really can't believe in God. In fact, not Charles Darwin, Richard Dawkins, he said, you know, that the homosexuals have come up with a great name for homosexuals, the gays. And this is such a happy term. We need something like that for atheists, that believe in evolution. And what they came up with was the Brights, believe it or not, the Brights. So they were people who were really bright. They were really, really smart. So Dawkins proposed this as a label for atheists who believed in evolution, Darwinian evolution, and it never caught on because everybody made fun of it. Because who wants to be called a bright, right? So anyway, so this is Laplace. This is the smackdown of Laplace's determinism, in that again we just don't know what's going to happen from the present in the future, because that's what Rice's theorem said. That's what the halting problem says. Okay. Uh, Foundations of proving non-computability. I asked ChatGPT to illustrate a Emo Phillips joke. And I like this Emo Phillips joke. It says, a computer once beat me at chess, but it was no match for me at kickboxing. So I asked Chat to generate a picture of Alan Turing drop kicking his computer after he got beat with chess. So that's my humor right there. Okay, so let's go on. What is the reason that all of these things can be proven? The reason is the reductio ad absurdum smackdown, or proof by contradiction. And it applies something which is called meta-analysis. And when you apply meta-analysis and something contradicts itself, it's an intellectual illusion. Let's go through illusions really quick. You know that there's optical illusions. You can see the optical illusions. To the left is a picture by Escher, which is just wonderful. It's guys which are climbing stairs, but you'll notice that even though the stairs look like they're going up and down, they actually repeat each other. It's an optical illusion, right? They're just going around and round in circles, even though the optical illusion says, well, no, they're not. You go up the stairs and up the stairs and up the stairs and up the stairs, and you're back where you started from. So clearly this is an optical illusion. So Escher used a lot of these mathematical sort of constructs in his art. Very, very fascinating. And then there are the pictures in the upper right. Mad Magazine. I used to read Mad Magazine when I was a kid. They called the picture on the left the three-legged Poiut, and it was spelled. Whoops, I'm sorry. Poiuyt, and they were really lazy because they just went to the top of a QWERTY uh, uh, board, and they just went Poiurt, and that was it. And so that was a big deal that they had the three-ringed Poiut, and that was a big thing for Mad Magazine. And on the right, you basically have Escher's stairs of always going up, but really they don't go up. They look like they're keeping on up, but they are going down. So this is an optical illusion. We're all familiar with optical illusions. I actually came up with some very good optical illusions. Can anybody see the optical illusion on the left? It's a rough one. I'll tell you
You have
what.
to
What's that?
squint your eyes a bit for that.
Yeah, you squint your eyes. Does it help to squint? Yeah, usually should help to squint your eyes a little bit.
Yeah, it's two stones will cry out or something.
Yes, the stones will cry out. Very
Oh,
good.
nice.
It's very subtle, and if you make this picture smaller, it's a little bit more evident. But yes, the stones will cry out, which is a passage from Scripture where uh, it was said that if nobody worshiped God, the stones would cry out. So yeah, so that's really interesting, but it's very subtle. And if you can't see it, that's okay. It took me a little while. Here's another one. This is a great optical illusion, I think. See the three girls there? Now squint your eyes and you see a picture of Christ. Do you see it? If you squint your eyes, you see a picture of Christ. That was a mind-blowing optical illusion to me, where you had these three girls, and if you squint your eyes, you see a picture of Christ. Can anybody not see it? I think this one is more obvious, but you do have to squint your eyes a little bit. Okay, I'm assuming everybody can see it. Here's another one. This is kind of interesting. This is what happens is this figure is moved forward one little step and then it repeats. It goes step, 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 and it looks like everything is moving, but really nothing is moving. And you'll see that here. Tell me that's not cool. I don't know if you can see my cursor. I'm going to fix my cursor and you'll see that it isn't moving. Anyway, I found that fascinating. I found that fascinating. Could you hear the sound on that, by the way? You couldn't hear the sound. Bummer, bummer, bummer. Okay. Um, this is another one, and those are not changing. Those squares are not changing. I'll put my cursor at the bottom right of this one cube. And you can see that bottom right is not moving if you can see my cursor. Do you see my cursor? Whoops, there it went away. Okay, so that's another example of an illusion. Now, what I'm gonna have to do is I'm gonna have to stop sharing. Let's see, stop sharing. And then I'm gonna have to share. With advanced sharing. Okay, I thought there was a case where I could share with sound. Anybody know how I can share with sound? I guess I don't see it here. Okay, you'll have to get this with the slides, which I've made available on the spreadsheet. You can download them if you want to. So let me share again. So I'll play it and give me a nod or a shake whether you can hear it or not. No? Okay. If you listen to this, you find out that indeed it's a tone which always seems to be going up. It goes, ooh, but it does it forever. So it is an audio illusion, and it keeps on going. And it's called a glissando. Somebody's named glissando, and if you're able to download the slides, you can listen to this glissando of a tone that seems to be rising forever. It's an audio illusion. Then there is if you will, the logical illusion. The classic one is a verse from Titus 1:12 in the Bible, the letter of Paul to Titus. He said the Cretans are always liars, and he was actually referring to a guy that we know in history. His name will come up here in a minute. I forget it, but let's extend this. If we have a Cretan, and let's assume that he extends this, and he doesn't say Cretans are always liars. He says everything I say is a lie. So this Cretan is saying everything I say is a lie, and we're going to come up with a logical illusion here. Everything I say is a lie. Well, if he says everything I say is a lie, he just lied. So he's telling the truth, right? Because we have to apply this in a meta-analysis. Meta-analysis means you take a statement and apply it to itself. So when we say everything I say is a lie, if we apply that sentence to what he said, he's telling the truth. Well, if he's telling the truth, he just lied. But if he just lied, he's telling the truth. So you have this back and forth, up and down sort of logic. It's a classical Cretan's paradox, and it doesn't resolve itself. It's like playing ping pong. You have no resolution at all, and the fact that you have no resolution reveals it as a logical illusion. And what about logical illusions? Well, audio illusions don't exist. They're an illusion. Optical illusions don't exist. They're an illusion. Logical illusions don't exist. They're not true. They're an illusion. So the Cretan's paradox, everything I say is a lie, is not good. So around and around we go into what I have heard called a strange loop. In fact, I think, yeah, here, if you're interested in reading a book that goes through this, Gödel, Escher, and Bach, and he goes through the different types of illusion. A very interesting book if you're interested in such things. Okay, a Cretan, everything I say is a lie. Here's an interesting paradox. You meet these two guys in a row, and it turns out that they're twin brothers, and one of them never lies, and the other one always lies. So they're both holding up signs, and they're both telling the truth. The one that never lies is holding up a sign that says, I never lie. The one that always lies is holding up a sign that says, I never lie, which is lying. And so these are two guys, and you have to ask them the right way to get to, I don't know, Corinth. You come to a fork in the road. And it turns out you can ask the guys one question. We can make up reasons why you can only ask one question. But you can ask one question to one of the brothers, but you don't know which one it is. So even though you have somebody that never lies and somebody that always lies, you can still get truth out of them, which is just fascinating. So how do we find out the right road? So there's a road going to the right and there's a road going to the left. And which one is the one that we take? So if we ask the lying brother, he'll point us to the wrong road. If we ask the truthful brother, he'll point us to the correct road. So the answer is at the bottom of the screen, and you really have to scratch your head on this one. It's a very interesting meta-analysis. You take one of them aside. You don't know if it's the liar or it's not the liar. But you take the one aside, and he said, if I ask your brother which road leads to Corinth, what would he say? If I ask your brother. Now, if you ask the guy that always tells the truth, you know his brother lies, so he's going to point out the wrong road. Again, if you ask the guy who always tells the truth, you know his brother would lie, so he would always point out the wrong road. If you ask the brother that always lied, he would point out the wrong road. If you ask the brother that lied, he would point out the wrong road. So both brothers point out the wrong road. Wow, that's kind of cool. Doesn't matter which one you ask. So you know which you ask this question, and whichever road they identify, you take the other road because you know that's the road to get you to Corinth. And so that's a way you can actually extract truth if you have opposing sort of contradictory sort of people. So that's really interesting. So you can also show that this idea of a logical illusion applies to philosophy and how to debunk philosophy. You might come up with people today, this is very popular, there's no absolute right or wrong, all is relative. They believe that, well, you have your truth, I have my truth, everything is relative. And then you ask them, well, you say, I disagree. And then he says, well, you're wrong. And you're right. So you notice what's happening there. The guy is applying the idea of right and wrong to the defense of his own philosophy. The guy is applying the idea of right and wrong to his own philosophy. Notice this is meta. This is the idea of taking a foundation and applying that foundation to itself. This is the foundation of some very important terms in mathematics and is foundational to algorithmic information theory. There is absolutely no right or wrong. All is relative. You say, I disagree. He says, you're wrong and you're right. And he says, absolutely. So the guy says he's absolutely right, that there is no absolute right and wrong. That is absolutely correct, that there is no right and wrong. So again, it's contradictory. It's called a self-refuting statement. It's a statement that refutes itself. It is an optical, not an optical, but a logical illusion. Therefore, it doesn't exist. It's just a stupid, vacuous thing to say. There is no absolute right or wrong. Here's another one. Uh, Michael Ignor just had a debate with the guy that's head of the Skeptic Society, which is a bunch of atheists that don't believe in God. And they believe that I'm skeptical of all things. And Michael Ignor in this podcast actually asked the guy, Michael Shermer, he says, well, you're skeptical of all things. Are you skeptical of your skepticism? And the guy fumbled a little bit and he says, no, he wasn't skeptical of his skepticism. He thought his skepticism was truth. So he wasn't skeptical of all things. He's just skeptical of things that didn't beat his ideology. Uh, so that itself is a self-refuting statement. If somebody says, I'm skeptical of all things, the statement refutes itself. Here's another one. This is one that was, what was his name? I forget the guy's name. He's a professor of chemistry at Cornell. That says only things proven by science can be believed. Now you've heard of this. This is the idea that science has replaced God. This happened in the church at the time of Darwin because Darwin came out and said, because of evolution, you don't need to believe in God. It's not true. Um, I have a good friend over in biology that is a Darwinian um, uh, adherent who goes to my church. You know, he's a wonderful Christian man. But only things proven by science can be believed. And you hear this said by the radical new atheist that you have to have science to back things which are true. The interesting thing about that statement is, again, it is a logical illusion. Only things proven by science can be believed. Can you prove this scientifically? You cannot prove scientifically that only things proven by science can be believed. Therefore, you can't believe only things proven by science can be believed. It is a self-refuting statement. Only things proven by science can be believed. Can you prove this scientifically? Absolutely not. So therefore, it must not be true, even by the statement. So the statement basically says by itself that that you can't indeed prove that things proven by science can only things proven by science can be believed. So therefore, it is an optical illusion. It's meaningless. It's without worth. It's a fantasy. It's a play on your soul, if you will. Now here's one that I ran across. My favorite comedian in the world is Emo Phillips. In fact, later this month, I'm going to go to Dallas with some of the members of my family and watch Emo Phillips at a stand-up comedy club. He is just genius in terms of his humor, and I think is maybe the greatest jokester living, maybe of the 20th century. Anyway, he has a Twitter page, and he saw this quote and he said something interesting. Bertrand Russell, by the way, wrote a book, Why I'm an Atheist. And he was an atheist, and he thought himself above other people. And one of his quotes was, the trouble with the world is that the stupid are cocksure and the intelligent are full of doubt. Now, can anybody guess how this is a self-refuting statement? Emo Phillips says, well, that sounds pretty certain about that. So by saying that absolute statement, he's kind of saying that he is stupid because he was not he was not full of doubt. I thought that was just a genius response. So do you see that as a self-refuting statement? The trouble with the world is that the stupid are cocksure and the intelligent are full of doubt. And Emo Phillips says, well, it sounds like you're pretty cocksure about that statement. And he was. It was an absolute statement. So I found this to be a very incredibly insightful comment by my comedic hero, Emo Phillips. Here is one. I wish I could play the clip for you. If you look at it, there's a little clip up here. But Deepak Chopra was one of these new age sort of gurus that comes around and talks about new age and stuff like that. And they took a Q&A at the end of the statement. And a man got up and asked a question, this man in the shirt here, the man in the red shirt. Now, you stated before, and he stated in his statement, that all belief is a cover up for insecurity, right? So if you believe in God, you're covering up for your insecurity. That's what he was trying to get to. And Deepak said, yes, I did say that before, that all belief is a cover up for insecurity, right? And the man says, do you believe this? And Deepak said, yes. And the guy said, thank you, and went and sat down. And it was a mic drop moment because all of a sudden everybody got exactly what that man had revealed. That indeed, if you apply Deepak's statement to himself, that he believed his statement, that belief in that statement was a cover up for his security. So that was another just beautiful, beautiful meta analysis where you take a statement and you apply it to itself. You take a statement and apply it to itself. We'll see this in Gödel's theorem. And by the way, here are some of the reactions. This is one of the guys on the stage in the bottom left, just cracked up. He thought it was hilarious that this guy had really cornered Deepak. And Deepak isn't as happy. You can see his reaction here on the bottom right. So he's not a happy guy that his idea was proven to be a logical illusion. Well, maybe it wasn't a logical illusion. Maybe it did show that Deepak was insecure. Who knows? So reductio ad absurdum proofs are proofs by counterexamples, if you will, by logical illusions. Here is a fun example, and that is my proof that all positive integers are interesting. Now, this is kind of a vague English word, but this is kind of a jokish sort of proof. All positive integers are interesting. Can you prove that all positive integers are interesting? Usually what you do in proof by counterexample is you assume the opposite and show it leads to a logical illusion, show that it leads to a contradiction, if you will. So all positive integers are interesting. So let's assume the opposite. Assume there is a smallest uninteresting positive integer. So if there are uninteresting positive integers, there is a smallest uninteresting positive integer. You ready for the punchline? That's interesting. Okay. So therefore, it's a contradiction. Now, again, this is a joke. Don't take it for mathematical certainty, but it really illustrates the idea of using the idea behind meta-analysis and applying a statement to itself. Very, very important. Here is the genesis of algorithmic information theory. It starts with Kurt Gödel. I got called by one time. He says, "You said Kurt Gödel. A girdle is an undergarment for a woman, and its name is Gödel. You have to do the O umlaut. So I've been trying to do Gödel. I don't know how well I'm doing it, but that's what it is, the umlaut in the O, Gödel. And then he published this paper in early 1930s, and then Alan Turing came along, and he actually gave examples of this, and that was indeed the halting problem. And with the halting problem, he actually invented the first computer. And then there is Gregory Chaitin, who came along afterwards and helped found the area of algorithmic information theory. And this was really this was really interesting. And we're going to go through the work of each three of these people in the development of algorithmic information theory and how it helps us to think about how complex things are. So we'll start with Gödel. Gödel, it turned out, was a Christian, and after his death, he actually proved the existence of God. If you want to look at this, and you want to go to Wikipedia, it's on Wikipedia, it's called Gödel's ontological proof, but he actually gives a proof that there's God. So if if you are a theist and you believe in God and somebody comes along and says, well, there is no God, just show them and I've done this. It's kind of hilarious. Just show them this. Here's mathematics that shows that God exists. Take a look at it. If you have any questions, let me know. Okay. And I actually did a podcast with Sam Haug, who actually went through each step of this and actually showed it. It's actually placing into mathematics a proof of Aslam. Is it Aslam or Anselm? It's one of the two. But he had an ontological proof of the existence of God, and Gödel took it and he actually made a proof out of it. And you can see the bottom line. The bottom line in terms of logic says, and therefore the backwards E, there exists an X so that God is X. So that was his final conclusion. But there's kind of axioms in the development of any logical proposition. There's axioms, theories, and other things. But this is not what Gödel was known for. By the way, he was known for being buddies with Albert Einstein. He spent the last days in the Princeton Institute, which is where great geniuses go. And they're such geniuses that Princeton says, tell you what, I'll cover your livelihood. You can live here, you can work here, and we'll foot all the bills, and you just have to do great and wonderful things. So this was after Einstein had developed his theory of relativity, his general theory, and his relativity, and this was after Gödel made his breakthrough in the early 1930s about his so-called incompleteness theorem, which toppled a big area of mathematics. So they were both buddies, and they used to walk together in the Princeton Institute. So the halting problem was the first popularized example of Gödel's proof. Gödel made his proof in 1931. By the way, he did not no, he was kind of a nerdy little guy, kind of quiet. And he came and he presented his paper at a conference. And, nobody paid any attention except for one guy. And that guy was maybe one of the greatest geniuses of the 20th century, and that was John von Neumann. John von Neumann went to his talk and he understood it. And he said, this is incredible. This is astonishing. But Gödel's theorem was basically from any set of assumptions, there are truths that cannot be proven. There are things that cannot be proven. This is really astonishing. Gödel was not a mentally healthy man. He died starving himself. He thought everybody was trying to poison him. And in my podcast with Gregory Chaitin, he talks about the time he spoke to Gödel and set up an interview with him. But he was a germaphobe. He was afraid that the food was trying to kill him, so he basically starved himself to death. I think that insanity goes with genius sometimes. And I love this. This is from the I forget XYK. There's some sort of comics, and I'm sure that you've seen this. And this kind of shows that the idea of optical illusion. He says, hey, Gödel, we're computing a comprehensive list of fetishes. What turns you on? And Gödel says, well, anything that's not on your list. Well, think about that. What turns you on? Anything not on your list. So they can't put them on the list, right? So they can't make a total list of things which are people's fetishes. Really, really ingenious. He can't respond to that. Really, really fascinating. Okay, I want to give you Gödel's proof in a nutshell. His actual proof involved the use of prime numbers and really ingenious use of prime numbers, but I'm going to give you the bottom line. He says that in any complete system of computation, that you will eventually get to what I'm going to call here theorem X. And he showed that theorem X was that theorem X cannot be proved. First of all, notice the meta-analysis. The theorem applies to itself, right? That's what we saw in the meta-analysis, that the idea applies to itself. And that's exactly what he's doing here. Theorem X cannot be proved. Well, here's two things which can happen in the derivation of a mathematical model. it can be complete, and this indeed was what it was happening in the early 1930s with Russell and Whitehouse. They thought that they could derive all mathematics through fundamental axioms and then develop from those axioms all of mathematics. And they published 2 volumes, 2 thick volumes, and they got up to 1 + 1 = 2 or something like that. It wasn't very fast development of accomplishment. But Gödel came along and he says, no, you can't do that, because I'm going to show that you can't, because there's going to be some things that you can't prove. And it totally derailed the work of Russell and Whitehouse and or Whitehead. I'm sorry, Whitehead, and totally put mathematics on a new road, which says there are some things which can't be proven, because again, Gödel said, no matter what math you start with, if it's foundational, you're going to get to a point where you get to a theorem X, which says the theorem X cannot be proved. Let's follow the consequences of theorem X here. If we don't prove theorem X, the system is incomplete. That means there are truths. Theorem X is assumed to be true in this case, but if we can't prove it, the system is incomplete. There are things which we can't prove. And so if we don't prove theorem X, the system is incomplete. So it means there are things which cannot be proven. It is incomplete. If we prove theorem X, then the system is inconsistent, because proving theorem X would be contradictory to the theorem. So we can't prove theorem X. So there's one logical conclusion. And the one logical conclusion is we cannot prove theorem X and accept the fact that the mathematics that is developed is incomplete, because we can't accept the idea that it's inconsistent. We don't want a system of math which is inconsistent, which says that 2 + 2 is 3, but 2 + 2 is also 4. We can't accept things which are inconsistent. So if we're going to assume that it's consistent and that everything that we've developed is righteous and wonderful, then the only thing that we can assume is that we don't prove theorem X and the system is incomplete. So therefore, there are ideas beyond the axiomatic development of the entire world of mathematics which are beyond our belief. Really an astonishing result. And so the conclusion, of course, is that this is incomplete, that the system is incomplete. Really fascinating. Now, all of you have heard about the theory of everything in physics. They're trying to come up with a single theory of everything, which describes all of the forces and everything in physics. And I guess the big one right now is the gravitational waves. In fact, it was Sam Altman that says if AGI could decide about gravitational theory, gravitational waves, and incorporate it into the theory of everything, we could truly say that artificial general intelligence was creative. And I agree with that, but it'll never happen. And so that's a separate topic for a different time. But somebody that recognized this was our old friend Stephen Hawking. Hawking said, I don't think a theory of everything actually exists. And this is something that he said. Up to now, most people have implicitly assumed that there is an ultimate theory, and we will eventually discover it. Indeed, I myself have suggested we might find it soon. He went on to say, maybe it is not possible to formulate the theory of the universe in a finite number of statements. This is very reminiscent of Gödel's theorem. This says that any finite system of axioms is not sufficient to prove every result in mathematics. So Hawking recognized the genius of Gödel and actually abandoned, or he gave doubt, I should say, to the development of the founding of the theory of everything, because he recognized that even if they did solve this final step, this gravitational wave sort of idea, that that there still might be things which were outside of that physics which were non-provable.
To ask the question. Hello.
Yeah, go ahead.
Okay. Wasn't sure if I could hear me, but so finite axioms. Could you define that as a finite system as well? Just I'm making sure that I'm making that connection.
Yes. If you look back at the classic work of Euler, you find out that he started with 5 axioms. And these were things which were kind of obviously true, that the closest distance between 2 points were a line, and I forget the other axioms, but they were kind of obviously true. And you have the axioms of Kolmogorov. Kolmogorov, unrelated to Kolmogorov complexity, developed the axiomatic theory of probability, because up to that point it wasn't a defined field. And so he was able to derive from axioms. I believe there were also 5 axioms there of the development of probability. We also have this with set theory. Cantor came up with an idea of set theory. Russell came out with a counterexample, and if I had time, we'd go through that. That's a really interesting thing because it is a reductio ad absurdum observation. And it turns out Cantor's theories of sets could not be done. So somebody went back, and I forget their names, and they actually started an axiomatic development of set theory, which kind of left Russell's contradiction out. So yeah, axioms are a statement of a number. It's a list of things which are assumed to be true and are hopefully intuitively true, like the distance between 2 points is a straight line. So when Russell and Whitehead, that's a terrible name, isn't it? Whitehead, named after a pimple. It turns out that Russell and Whitehead in their work actually developed a number of axioms. I don't know what they are. I've seen the books. They're really 2 thick books, and they are said to be the most important books written in the 20th century that nobody has read, because it's just page after page of terrible, terrible mathematics. And so therefore, yeah, that's the assumption. This was an assumption, by the way, put forward by David Hilbert. David Hilbert says we must know everything. And he thought that we could come up with axioms which could develop the theory of entire mathematics. And I believe in the early 20th century, he presented a list of problems which were still open in mathematics. And one of them was development of a theory that says all theory can be developed by some fundamental axioms in mathematics. And that's the tool that Russell and Whitehead grabbed onto. And they began to try to answer Hilbert's problem, but they ran into a problem when Gödel showed that no, it wasn't possible. So that's what we mean by an axiomatic development of the entire theory of mathematics. Does that make sense?
Yes. I was just more clarifying the statement was with the finite axioms you cannot completely know everything within that system.
Exactly.
Okay.
Exactly. And that turns out to be foundational with algorithmic information theory.
Okay. Thank you.
So this was a puzzle. If I remember right, Russell had a barber named Barry. And Barry came with him with a very interesting self-refuting statement. He said, let X be the smallest positive integer that requires more than 20 words to define. Isn't that an interesting definition for a word, for a number? Let X be the smallest positive integer that requires no more than 20 words to define. Huh. Well, Russell noted, and then Barry said, this is a weird thing because guess what? If X is the smallest positive integer that requires more than 20 words to define, that statement itself defined X. And it defined X in 15 words. X is the smallest positive integer that requires more than 20 words to define, defines X in 15 words. That's Berry's paradox. And it is a self-contradictory statement. It is a logical illusion. It actually makes no sense to say that because you've contradicted your statement using 15 words. Anyway, that's Berry's paradox. So let's get to the idea of, by the way, I'm going to go a little bit long here, and I'll tell you the reason I'm going long. If you'd like to stay, that's certainly invited. If you'd like to bounce, that's okay too. This will be posted. So let's talk about the Turing halting problem. Here is the Turing halting problem. This is basically Turing's proof, and I'm going to use a lot of pictures. We're assuming that we have a halting oracle here. So we're going to assume that a halting oracle exists, and then we're going to show by a logical illusion, by a reductio ad absurdum smackdown, that this cannot exist. So the idea is that we have this program H of pi. That's H, and P is the program inside. I is the input into the program, if you will. So we have H, and we have P, and we have I. And this is our halting oracle. So if we present it with an input and a program P, can you see my cursor? Okay, I hope you can. If there's an input I and a program P, then you present this program and this input onto this halting oracle, and it will tell you it will halt or it will loop. H is for halt, L is for loop. Okay? So we're going to assume that that exists. Okay. Now, if this exists, this is a piece of code. And this piece of code can be represented as, it can be replicated here. And here is this piece of code. Okay. And here is this piece of code. And it turns out that both the input and the program are expressed as a sequence of ones and zeros. We'll assume that. And I think we can all agree with that. So we're going to actually have the input and the program be the same thing. So H of P with an input of P. And we're going to look at whether that program halts or goes forever. So we're going to present it, and it either halts or it doesn't halt. Now, again, this is a piece of software. And we put in this P, we get that it halts or it doesn't halt. Well, if it halts, we're going to hook it up to a looping program that loops forever. We might put a while loop, for example, while 1 is equal to 1, and that will loop forever, right? And then if it says it's a looping program, we give it a halting program. This should be where while 1 is not equal to 1, which will halt immediately, right? So if it halts, we feed it into a program which loops forever. If it loops, we feed it into a program that halts. Now, if this program halts, then this overall program halts. And if the looping program happens, this program loops forever. So you get the idea? P goes into H of PP. It either halts or it loops. If it halts, we feed it into a looping program. If it loops, we feed it into a halting program. So the program halts in this case, and it loops in this case. Really fascinating. So here's a question that that he asked. What if we, instead of, okay, over here we had P, right? What if instead of P, we put in N? Because N is just a string of ones and zeros too, right? So we're going to take P and we're going to replace it by N. So N is just a program of ones and zeros. So we're going to replace it by N. So therefore, we get the halting program with H of N and N. Notice again, self-reference. Self-reference is important for these logical illusions, for this reductio absurdum smackdown, for these proofs. So we feed N into the halting problem. And again, if it'll either halt or it will loop. We're not sure which. If it halts, if the halting oracle says it halts, we run it to a looping program. If it loops, we run it into a halting program. Well, here's the problem. Let's first of all say that the halting oracle says that h of nn halts. Well, if h of nn halts, then we come up here and we start this looping program, but you can see in the upper right-hand corner that the program actually loops. We have a difference between the output of the halting program and the actual program. The halting program says it halts. The looping program says it loops. That can't be. It's either one or the other. It either halts or it loops. It can't do both. So again, if we put this in and it comes up here and it says the program halts, then that program halts will initiate a looping program, and that program will loop forever. The contradiction is that the halting oracle says that the program will halt, and the overall program says the overall program actually loops forever. The halting oracle is wrong. The program is going to loop forever. Now we can also go down to the other action. What if n says that the program loops? So we feed it the input n, the program loops, we go down here, and if it loops, we go into a halting program while 1 is not equal to 1. And of course, this is going to halt, and so it halts. So the halting oracle says that the program is going to loop forever, while the actual program halts. So in both cases, we have a contradiction of the halting oracle and the output of the machine. I think that that's just fascinating. Again, up here, if it halts, it loops. The halting oracle says it halts, but in reality it loops. Down here it says the program loops. The halting oracle says it loops, but it actually halts. This is a logical illusion, which shows us that our initial assumption that there exists an H, a halting oracle, has to be incorrect because it leads us to a logical illusion. It leads us to a something which doesn't exist. Now, if we did have a halting oracle, I'd love to talk about this. This is really interesting. There are a number of open problems. And by the way, one of the things that Gödel showed is he showed that we might have some things that are true just because they're true, and there might be other things which are true because the proof hasn't been discovered. If you look in, I go into, I think it's Quora, and it gives like breakthroughs in mathematics. Like there was this girl, her name was Cairo, and she disproved a conjecture which had been around for 40 years. And there's been other conjectures which have been around for many, many years. There's Andrew Wiles, who a couple of decades ago showed Fermat's last theorem. And he proved Fermat's last theorem after spending 7 years in his basement. It was such an incredible accomplishment that they made a musical out of it. And if you want to watch it, it's on YouTube. It's called Fermat's Last Tango. So it's a musical, and it has all sorts of interesting things happen. Well, here's some problems which are still open. Some of them have $1 million prizes associated with it. There's Goldbach's conjecture. In 1742, he wrote a letter to Euler, and Euler was in, and by the way, if you listen to Gregory Chaitin's interview, he agrees with me that Euler was the greatest mathematician of all time. He was just astonishing. Euler wrote a letter to Goldbach wrote a letter to Euler, and he says, all even numbers greater than 4 can be expressed as the sum of 2 prime numbers. This is something which is not obvious. But if you start examining it, 32 is equal to 29 plus 3. Both of those are prime. Okay. 144 is equal to 131 plus 13. Both of those are prime. 8 is equal to 5 plus 3. And if you get to bigger numbers, it works too. 15,748 is equal to what you see here. 7829 plus 7919, both of which are prime. So that was Goldbach's conjecture. Euler looked at it and he says, man, primes are really rough. And there was really interesting time. It turns out that Friedrich Gauss was just enamored with prime numbers. And he computed the first 1,000 prime numbers by hand in order to analyze them. Just a crazy guy. Okay, and then there's Legendre. By the way, Notice that in order to disprove Goldbach's conjecture, we only need one counterexample. If you can give me an even number which cannot be expressed as the sum of two primes, we've disproven it. If we prove it, we have to prove it for all even numbers, but there's an infinite number of even numbers, so we'll never be able to prove it. Then we have Legender's conjecture. Does there always exist at least one prime between consecutive perfect squares? Like 3 squared plus 4 squared, you have the 11 is between there, and 8 squared, 9 squared, 71 is a prime between there. So you take any two consecutive numbers and you square them, and there's a prime number between the two. That was his conjecture. It has not been proven. It has not been proven. And then there's the Riemann hypothesis. This is the biggest holy grail of mathematics right now. And it holds a $1 million prize from the Clay Institute for the first person that proves Riemann's conjecture. Now remember, Riemann's conjecture might not be provable. There could be some of these things that are true because they're true, and they're not provable. They're beyond our reach of our current mathematics, according to Gödel. And so that's fascinating, but nevertheless, people are trying to figure this out. So there's something called the Riemann zeta function, which is shown here. And I won't go into the details because they're kind of ugly, but it says that basically that all of the non-trivial zeros lie on the imaginary axis. And this has been checked for the first 10 million non-trivial zeros. So they've shown the zeros of this. You know what the zeros are. That's where the function goes through the x-axis, if you will. And $1 million prize is offered by the Clay Mathematics Institute for the first correct proof of the Riemann hypothesis. I don't know if anybody of you have watched the movie A Beautiful Mind, which is a story of John Nash, a Nobel Prize winner, who was a genius in mathematics, but also I don't know, he had mental problems. He always thought he was being followed around by somebody that gave him advice. And I actually read his biography. I read the biography of A Beautiful Mind. He did not have a beautiful mind that was expressed in the book. He actually had a reprobate mind, not very good. And anyway, in the movie, he talks about the Riemann hypothesis very briefly. He talks to a student and says, don't spend your time working on the Riemann hypothesis. It turns out a lot of mathematicians have done it and wasted their careers trying to prove it. So it's made its way into the popular literature. So there's Riemann. And so here's the interesting thing. If we had a halting oracle, suppose we did have a halting oracle, we could all write a program that checked consecutive even numbers. We start out with 4. Yeah, let's see. 4 is 2 plus 2. Those are prime. 5. Yeah, 3 plus 2. 7. Let's see. 7 is 2 plus 5. And so we begin to loop through all the even numbers, looking at each case, whether or not there are 2 primes below that number, which add up to that number. And if we find a case where that isn't, guess what? We stop the program. Say, we have found a counterexample. In this program, we kind of loop and loop and loop and loop, and it does one of two things. It loops forever, it doesn't halt, or after a while it'll stop, said I've found a counterexample, and here it is. So this is a problem that if we had a halting oracle, we could just present our program to the halting oracle. If the halting oracle says this thing loops forever, then Goldbach's conjecture would be true because there are no counterexamples. It loops forever. It doesn't halt. If, on the other hand, it stops, then it's found a counterexample and Goldbach's conjecture is wrong because we found a counterexample. So again, this is something I think we could all write in Python or any program that you want to. Write a program, give it to the halting oracle. If it halts, the counterexample is wrong because we found our single counterexample. If it doesn't halt, the conjecture is proved because it runs forever and there is no counterexample. And this is the same thing which is true for the other things. It's true for Goldbach's conjecture, the Legendre conjecture, the Riemann hypothesis. All of these can be written in a looping fashion to see if there is a counterexample. And if the program never halts, then the proposition is true. If it halts, they've found a counterexample and the conjecture is incorrect. So you see, the power of the halting problem is astonishing. We could prove all of these different things. We could prove all of these with the halting oracle, prove or disprove. And there's other things. There's other conjectures out there. And there's actually a Wikipedia page of unproven mathematical results. There's Andrica's conjecture that states between the square root of Pn plus 1 and P sub n that this is always less than 1, where P sub n is the nth prime. Brocard's conjecture. I love this one, the Collatz conjecture. There's been a lot of people that have looked at this, including some of the current big mathematicians. If you take the difference equation, x sub n plus 1, if it's odd, you multiply it by 3 and add 1. So you make it bigger. If it's odd, you make it bigger. If it's even, you make it smaller. You divide it by 2. And it is not apparent at all, but this looks like it always converges to 1. And every number they've ever tried it for, you can start it with any number for x sub 0, and this iteration will always converge to 1. Just an astonishing result. Astonishing result. And here we get into Kolmogorov complexity. And I think this will be the last piece of slides that I give to you. Kolmogorov complexity is based on the idea of the smallest descriptive length. For example, I ask you to generate a program to generate pi, to say 20 significant figures. And I write a program to generate pi to 20 significant figures. Guess what? One of our programs is going to be shorter than the other one, right? Obviously, one of our programs is going to be shorter than the other one. Now, we know that the shortest program is greater than a bit, and we know that the shortest program is less than the shortest program that we know about as of yet. But this leads us to the conclusion there exists a shortest program. There exists a shortest program to compute the number pi. And that shortest program, as measured in its length in bits, is the Kolmogorov complexity of the number pi to that number of significant bits. There exists a shortest, Chaitin called it an elegant program. This is the Kolmogorov complexity. And there exists no computer program to detect the shortest program. So we can never tell. This is something that, again, is non-algorithmic. We cannot tell the shortest program to generate the number pi to 20 significant figures. The best we can do is bound it. We ask 1,000 people to write the shortest program they can to compute pi to 20 significant figures. And then we look at the shortest one, and either that's the result, or maybe the elegant program, the shortest program, is even shorter than that. And this is not true, of course, for really, really short programs, but you get into any degree of complexity, and you're not going to be able to do this. So here is Chaitin's proof, and we'll end with Chaitin's proof because I think it's beautiful. First of all, we have to recognize there are an infinite number of elegant programs. For example, if I ask the elegant program for pi, and then I ask the elegant program for e, that has a certain length. If I ask the elegant program to generate both pi and e, that's going to be a longer elegant program, right? And it turns out there are programs of arbitrary length which are elegant. It goes on forever. And you can construct those by just superimposing problems of lower length, if you will. So there are an infinite number of elegant programs. So we have to remember that. That's very important. There are an infinite number of elegant programs. So we're going to do this, and this again is Chaitin's proof. We're going to assume that we have a program, and we're going to present it to an elegance tester. And the question is P elegant? Is this the shortest program to generate what it generates? And the answer is yes or no, or bogus. You know, we can give ones and zeros and it just doesn't compute. It's just a bogus program. So yes, it's the shortest program, or no, it's not the shortest program, or it's bogus. It computes something else, or we just don't care. So we're going to assume that this elegance tester exists. And again, if it exists, then therefore we can put it in code. And let's assume that we have access to that code and we can replicate that code into a larger piece of software. So here's what we're going to do. We're going to take the elegance tester and we're going to ask, is P elegant? This is the ET. And we're going to start a counter. And by the way, the elegant program is not how long it takes to run. It is the shortest program. You could have a short program that runs for 1,000,000 years and it has a small elegant program. It isn't how long it runs, it's how short the program runs. So this counter here is going to be counting for a long time. That's okay, because we don't care about time. We only care about the length of the program. So we have this counter, and it turns out that this counter is eventually going to generate all of the available computer programs for a different for some sort of computer language. So we have a counter, and we have an elegant tester. Is P elegant or not? Okay, so this is actually another program. This is the elegance tester plus augmented with the counter. And this elegant program with the plus is actually, as you can see here, P is a bit which is P bits long, and ET plus, which is the number of bits for the augmented elegance tester, is ET plus bits, and so we're going to count the counter at whatever ET plus is. So maybe ET plus is, I don't know, 1,000,000 kilobytes or a million megabytes. So we're going to start the counter at 1,000,000 megabytes. And so it's going to start at 000 for 1,000,000, then 00001, 00002, and we're going to begin to check it. Now, eventually, if the elegance checker is right, it is going to find an elegant program which is longer than ET plus. Let me say that again. If this counter goes large enough, it is eventually going to find an elegant program which is bigger than ET plus, the length of ET plus. Well, this gives a counterexample. What is this counterexample? ET plus found the elegant program using fewer than P bits. So we're saying that this program might have the length of twice the length of ET plus. So P has twice the length of ET plus, and we say it's elegant. No, it isn't elegant, because ET plus generated that program. And not only do we know what the result is, that it's elegant, we have the program to do it, because we can go to the counter and we can extract the elegant program. So therefore, it's the same sort of thing. Eventually, this elegance tester is going to be testing things which are larger or longer in length than the ET plus length of the program. And therefore, the ET plus program found the elegant program, because we can extract that from the counter. Wherever we get a yes for that, we can go back to the counter and say, well, that's the program. And therefore, P cannot be elegant. So therefore, for programs of a sufficiently large size, that no, you can't, the elegance detector cannot exist, because we have found a logical illusion, a reductio ad absurdum smackdown, if you will, and that indeed can't be true. So that's the reductio absurdum smackdown. Okay, so that's it for the lecture. I do have some comments. Okay. I want to see if there's any questions. Okay, any questions at all? I hope I explained this, because this idea of contradiction becomes kind of a mind-boggling thing. I mean, even the Cretan's paradox was his, yes, he's lying, no, he's not lying. Yes, he's lying, no, he's not lying. It gets to be a little weird. And then we talk about some of the other logical illusions, and then showing that indeed that assumption of a Turing oracle or a halting oracle, if you will, results in a logical illusion, and showing that knowing an elegant program eventually results in a logical illusion, and that therefore the elegant program detector and the halting oracle are non-algorithmic and cannot be computed. Okay. We'll continue with this idea next time. Next time we'll delve into the idea of 3D printers. I know some of you in here, Rebecca, for example, knows a lot about 3D printers. And we asked the question, you're going to write a program for the generation of a bust of Lincoln from a given material. Okay, you have to assume the given material of the 3D printer. And then another program that generates a bowling ball. Which program will be longer? Clearly the one that generates Lincoln, because we have to get all of the wrinkles. We have to get the mole. He has a mole on his cheek. We have to get his hair. We have to get his beard. We have to get everything else. Whereas for the bowling ball, we just say print a sphere and put 3 holes and then describe the holes and we're done. So it turns out that the bust of Lincoln has a greater Kolmogorov complexity. Why? Because the program used to generate it is longer than the program used to generate the bowling ball. And this is the concept of Kolmogorov complexity. And we'll explore Kolmogorov complexity a little bit more next time. Any questions?
So Kolmogorov complexity is not just the shortest code. It is
the shortest close. Because Lincoln's bust for the 3D printer, there is a shortest program to generate that bust, right? And that shortest program in relationship to the programming code is the Kolmogorov complexity of generating Lincoln's bust. And there is a shortest program for generating the bowling ball.
So
and that shortest program just intuitively is going to be a lot shorter than generating the code for printing Lincoln's bust.
could that not be equated to the least amount of information to describe something?
Oh, exactly. In fact, it's Kolmogorov information. The length of the program is the shortest program is the Kolmogorov information of the object. Notice the difference between the Kolmogorov complexity. The Kolmogorov complexity looks for the shortest program, and we measure that shortest program in bits or bytes or whatever. On the other hand, Shannon information looks at things in terms of probability, right? We define information in terms of probability. So Shannon information deals with probability. Kolmogorov information deals with structures which already exist and how much and the degree of complexity that they are.
Okay. So you could describe that Shannon information is a quote forward-looking, as we are trying to describe things that I would say don't exist,
Right.
and Kolmogorov information are describing things that currently exist.
Well, that's true. Except now with Shannon information is defined in terms of probability, but you also have cases where you have a DVD or something like that, or you write a program and that's a certain number of kilobytes long. And so that's something which does exist, but we still borrow the idea of the probabilistic bit in order to describe that.
Okay.
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 Anything else? Okay. Thank you very much.